When people think about robotics today, they tend to think of hard and rigid metal structures driven by powerful motors. Many robots do in fact have hard structures which can make them heavy, slow, inefficient, expensive and potentially dangerous when it comes to working side by side with people. But what if robots could emulate humans or other creatures in nature? What if they could harness the manual dexterity of humans, the maneuverability of birds, or even change their surface texture based on environmental context? Unlike traditional robots, nature offers hard and soft structures, actuators, sensors, and grippers that achieve many of these capabilities. Soft structures and systems are also inherently safer when interacting with people. We are now seeing fundamental changes in the field where improvements in materials are literally reshaping robotics. The new trend is moving towards soft robotics, driven by improved capabilities, lower costs, and increased safety for human interaction. Electroactive polymer artificial muscles expand when a voltage is applied and contract when the voltage is removed, thus converting electrical energy into mechanical motion. Unlike other voltage-controlled materials such as piezoelectrics, artificial muscles have the force and stroke of natural muscles. These characteristics can enable robots to mimic the dexterity and mobility of humans. In contrast, pneumatics, a technology that powers most of today's soft robotics, requires noisy air compressors, hard-to-control valves, and awkward hoses. Another robotics trend enabled by electroactive polymers is the ability to change surface texture and even develop skins that can sense pressure and contact, which is particularly important as robots start to work side by side with humans. A driving force behind these new sensing developments is the need for wearable sensors that achieve comfort and function by matching skin independence. Because these stretchable polymers can also act in reverse with low hysteresis, meaning that it can generate power by being stretched and contracted while achieving consistent results. They can also be built into clothing and fabrics to measure motions and forces. The market is also starting to see soft grippers with new capabilities. Unlike their rigid counterparts, soft grippers can pick up a wide variety of objects with minimal sensing and control. An extreme example is found with jamming grippers, in which a flexible sac is filled with a powder-like substance that can conform around an object of almost any shape. A vacuum process then makes the soft gripper rigid, enabling it to pick up the object through friction, without any intelligence or complex processing. Electrostatic forces can be used to pick up and move objects that might be too delicate to squeeze with the forces needed to produce sufficient frictional forces. Similar to the principle of rubbing a balloon on hair to create electrostatic attraction, this soft and flexible technology allows for electrically controlled adhesion to grip almost any object. These robots can be used for inspection, surveillance, as toys, or even eventually for cleaning hard-to-reach places in buildings. And what if materials could change from soft to hard on demand? These materials, types of metamaterials or mechanical materials, are built of repeating elements. Connections within the elements can be changed by electrostatically clamping different layers together. Compared to more traditional smart materials and systems, electrolaminates use only low-cost and lightweight flexible polymers, offer far greater stiffness, variation, and elongation, and can react quickly. These characteristics result in lighter, cheaper, less complex structures that can absorb a great amount of energy. To date, we have demonstrated electrolaminate straps able to hold up to 150 pounds.